In this example, we will have another application of our method of being able to find critical points and test whether they're minimums or maximums. So we have a lidless box that is made by using 2 square meters of cardboard. We want to find the dimensions that maximize the volume. Okay, so we have a lidless box. It doesn't say it, but it's implied that it's a rectangular box. A cylindrical box would be much harder to work with. So we'll use X, Y, and Z right here. And it has no lid, so it's open on the top. Now, if you remember how to maximize, we have a constraint function and an objective function. The constraint is right here. We have 2 square meters of cardboard, so that's our constraint. Is that our surface area is equal to 2. Technically 2 meters squared, but we won't worry about the units until the very end. All right, so let's use that. So if the surface area is equal to xy, which would be the bottom part of this box, right? X times y, there's one bottom, plus 2xz plus 2yz. And we want to use that constraint. Oh, and we know that it's equal to 2. Sorry about that. And we want to use that constraint in order to fit into our objective function, because we know that we have an objective function, which is volume right here, right? So there's our objective function, the things we are trying to find the minimum or maximum of. All right, so if that's my objective function, then volume is what I'm trying to maximize. But volume is equal to x times y times z. I mean, it's really straightforward because it's a rectangular box. So I want to use this constraint, and technically I could kind of do it for any of the variables, but I just did it for z because I felt like it. So I said I took away xy from both sides, and I factored a z out over here. So z comes out of these two terms right here. It leaves you 2x plus 2y is equal to 2 minus xy, right? Because I've subtracted the xy to the other side. And therefore z is equal to 2 minus xy over 2x plus 2y. And then I will substitute that into my volume function that I'm trying to maximize or minimize, in this case maximize. And I will say my volume is equal to x times y times 2 minus xy over 2x plus 2y. Well, I mean, we could do this a couple ways, but I know that I need to be able to find the derivative of all this, so I'm going to distribute. I'm going to distribute xy to both of these things. So that'll be 2xy minus x squared y squared divided by 2x plus 2y. All right, now in order to find my critical points, I know that I need the derivative of this with respect to x to be equal to 0, and also the derivative with respect to y to be equal to 0. Okay, so let's start by finding v sub x. V sub x would involve the quotient rule. That's why I did this, because I didn't want to have a quotient rule and a product rule involved, so I thought I'd make it all just a quotient rule. So let's see, I take that denominator, so 2x plus 2y, times the derivative of the numerator with respect to x. So that's 2y minus 2xy squared, right? Minus, and then now I'll leave the numerator alone, so that's 2xy minus x squared y squared times the derivative of the denominator with respect to x, which is 2. And I put that all over 2x plus 2y. Now I know I need it to be equal to 0. And being realistic, it won't do me any good if the denominator is equal to 0. What I need is that numerator to be equal to 0. So I'm going to set the numerator equal to 0. Just on a side note, notice that 0, 0 would be a bad move, right? So if you have 0, 0 down here, you're going to have basically 0 over 0 is going to be a mess. Well, because you'd have division by 0 and division by 0 is no good. So just keep that in mind as we go forward. Okay, so let's distribute this numerator out. So that numerator would be 4xy minus 4x squared y squared plus 4y squared minus 4xy cubed minus 4xy plus 2x squared y squared. And that whole thing is equal to 0. Right? That's the only way I'm going to get a critical point, is if I can make this happen. Obviously, this is a little trickier to do than some of the ones we've done previously. And of course, we could always use maple a little bit to help ourselves if we wanted to. Well, a couple things I notice here. I have a 4xy up in front. That came from 2x times 2y right there, so that's a 4xy, and a minus 4xy back there, which came from this minus 2xy times 2. So those are gone. And then I noticed that the minus 4x squared and the plus 2x squared, minus 4x squared y squared and plus 2x squared y squared, those are like terms. So I can kind of combine those together. And let me rewrite this. This is 4y squared minus 2x squared y squared minus 4xy cubed. And there's a y squared and a 2 in everything. So I'm just going to factor that out. Wonderful. Lovely. Well, this is not going to happen, right? So this is not possible. You can't have y be 0. If y would be 0, I mean, we already knew it would cause the denominator here to be 0, and that would be bad. But also, it's a box. How could y possibly be 0 and you still have a box? You'd have a flat box. You'd have a flat piece of cardboard, but it wouldn't be a box. So this is actually impossible, just by logic, right? For a couple reasons, right? So it's a box. Not going to happen. All right, so that's out, and that leaves me this piece. So v sub x would be equal to, let me just say, so I need 2 minus x squared minus 2xy to be equal to 0. And then I need 2, I mean, let me just say, by logic, when you look at this problem, it was going to be kind of very similar, same kind of thing for v sub y, right? Matter of fact, it's going to be exactly identical because there's nothing special about the way we did v sub x here. So v sub x to be 0 means that we need this to be equal to 0. And then by logic, because we don't need to do all this over again, let's get real. We need v sub y, which would be the exact same thing but with y's, right? Would also need to be 0. So we can take maple and solve this. We could just set the two of them equal to each other, right? This actually is a really easy thing to solve once we know that this is true, right? So the only piece is that you have to do this by logic. Otherwise, you have to sit there and find v sub y. But it's literally going to be the exact same thing, but with y squareds wherever there's x squareds and vice versa. Okay, so now let's combine these two together. Let's take this piece, and let's solve. We know that v sub x and v sub y, v sub y, not y sub y, have to be equal to 0. Which would mean that 2 minus x squared minus 2xy would have to be equal to 2 minus y squared minus 2xy. And they'd all have to be equal to 0, right? All right, well, this is easier than you think because the 2's would cancel. If you subtract 2 from both sides, they're gone. The 2xy's will cancel, and you're left with x squared equals y squared, right? So that would mean that, I'll just write it this way. Technically, it's negative equals negative, but then you can switch them and make them both positive. And that would mean that y is equal to plus or minus the square root of, plus or minus x, not the square root of x. It's a square root of x squared. Here, I'll do it this way. Of course, because this is a box, the negative is again impossible because you can't have negative, let me just write that, negative x impossible, it's a box. You can't go back into like antimatter space to have an x value. So negative x impossible because it's a box. Okay, so that means that y is equal to x. So whatever these dimensions are, y and x will be the same. All right, so we're going to use that piece, and we're going to use the fact that y is equal to x, and then we're going to substitute into v sub x. So let me just do a little bit of work here. All right, so use the fact that x is equal to y, or y is equal to x, and sub into v sub x. All right, so v sub x is back here, right? Kind of in the end, it kind of all came down to this piece right here. So v sub x is equal to 0, right? Which we knew. So that means that 2 minus x squared minus 2x times x is equal to 0, which would mean 2 minus x squared minus 2x squared is equal to 0, which means 2 is equal to, this is 3x squared. So 2/3 is equal to x squared. X is equal to, and again, it's plus or minus square root of 2/3, which if you multiply both by the square root of 3 over square root of 3 is plus or minus square root of 6 over 3. However, again, it's a box. Can't have the negatives, right? So that's not even worth bothering about. And then once we know x is 6 square root of 3, excuse me, square root of 6 over 3, it's meters because this was the meters of a box, then y is also, because y is equal to x, square root of 6 over 3 meters. There's 2 of our dimensions right there. I mean, that's what they wanted, right? They want the dimensions of the box with maximum volume. This is the only critical point. This is the only way that there's going to be a maximum volume. All right, now all we have to do is solve for z, right? Because dimensions are 3 dimensions. It's got 3 dimensions. It's a box. So we have 2 of them. We need the third one. So use x and y values and find z. Okay, well, let's see here. If you recall, way back at the top, we have a formula for z. Z is 2 minus xy over 2x plus 2y. So z is equal to 2 times x minus, 2 minus xy. I apologize. I was doing the denominator. 2 minus something over 2 times x plus 2 times y. So x is square root of 6 over 3, right here and right here. And y was square root of 6 over 3. And lo and behold, that's going to make z equal to here. I don't know why I'm doing all of this by hand, but here, 2 minus 6 ninths over 4 square root of 6 over 3. That's 12 ninths on that numerator, because that's 18 ninths minus 6 ninths, which is 12 ninths. And it's divided by, well, here, multiplied by 3 over 4 square root of 6. So when you cancel all of that, you get, let's see, 3, 3, right? So it ends up being just 1 over the square root of 6, right? Because all of that goes away. Meters. Or if you like, square root of 6 over 6 meters. There's your z. So this dimension right here, this dimension right here, and this dimension right here maximize the volume. So if you want to write it as a point, you could say square root of 6 over 3, square root of 6 over 3, square root of 6 over 6 meters maximizes volume. Now, I didn't bother showing the second derivative test because of this. This is an application. The only critical point possible that we are finding here is the only thing that will maximize the volume. So there's no point in even bothering to check, although you're welcome to. But I wouldn't recommend it because when you think about, we ended up in a world of fun with all of these second derivatives and derivatives here. So if we want to do second derivatives and all of that jazz, we could, but it's going to get us this, it's going to tell us that this is fine. The problem is that to do that, we would actually have to go back here and kind of simplify a bit, but we'd still have to deal with the 2y squared. It wouldn't be the equal to 0 part. So you'd have to deal with a pretty atrocious quotient rule to be able to find vxx and vyy, etc. And it's really not worth it because we know how this answer must work. This was an application with a real life problem. The only critical point that we find will be the maximum volume point. Now, of course, if you're concerned, I did check myself with Maple. Sorry, my dog barked there. All right, so here's the box right here. You can see I have the volume function defined right there, volume 6, V6, so because it was problem number 6. And then I had it find the derivative with respect to x, the derivative with respect to y. There they are. And then I had it solve them when they were both equal to 0. So I said, take this function, right, which was Vx, and take this function, which is Vy, and solve them both equal to 0 simultaneously. So I use the solve command, and it gives me these answers, which is fine, because all they really are is square root of 3x squared minus 2 and square root of 3x squared minus 2, right? Positive, negative. So I'm not worried about it. I knew that that was the 3x squared minus 2 that I came up with myself. And so then I solved that for x, and sure enough, I get my answers. And we know that the negative 1 is no good to us because we have a box with real life space. And so then I also could use Fsolve and find decimal approximations if that makes you happier. So if you use Fsolve instead of solve, solve gives you this root of answer, but if you use Fsolve, it's going to give you the decimal answer. And you can see that that's the same as if I use Fsolve on this particular equation. But either way, that gives me my x value. Once I know my x value, I know my y value. And then once I knew that, which they're right here, then once I know those, then we're all good. And I can find the z, no problem.